Okay, let's get started just so we can make sure our speaker has enough time to cover the material that she is after. Good afternoon and welcome to our virtual colloquium. If you're in or around Hanover, you are getting really sunny times, and so welcome to summer here. It's my distinct pleasure to introduce you to Professor Daryl Haggard, a dear friend of mine and all around good human and scientist. Daryl is an assistant professor of physics at McGill University in the McGill Space Institute and holds a Canada Research Chair in multi-messenger astrophysics. She studies the galactic center and Sagittarius star, electromagnetic counterparts to gravitational wave sources, accreting compact objects of all sorts, and my personal favorite, supermassive black holes and their host galaxies. And she does this all using multi-wavelength and time domain surveys. Daryl has had an incredibly rich educational history. She got her undergraduate degree in philosophy from St. John's College, then got a master's in physics from San Francisco State, and then earned her PhD in astronomy at the University of Washington, so seen a good amount of the country as well. She spent 4 years as a prize postdoctoral fellow at Northwestern University Sierra, and then a year on faculty at Amherst College before she moved to McGill. Her research accomplishments are many. She is a co-recipient of the 2020 Breakthrough Prize in Fundamental Physics with the EHT collaboration. I've changed my background appropriately. She's a 2020 McGill Principals Prize for Outstanding Emerging Researchers. She's a Kavli Frontiers Fellow. The list goes on, but I'll just mention my personal favorite in that she's been a NASA Jenkins pre-doctoral fellow, which is actually where we met many years ago. So thankful to have met her there. She also spreads the good word of astrophysics via outreach and press engagements and has been awarded the top 10 Discovery of the Year by the Quebec Science magazine. She does a lot of work on equity, diversity, and inclusion to maximize our excellence in STEM, both at our own institutions and with AAS. So in my opinion, she's the epitome of what it means to have significant impact, both within, on, and beyond the field. So it's my distinct pleasure to introduce you to Professor Daryl Haggard. But before I turn the floor over to her, for those of you joining in the audience, let me just give you a few housekeeping updates. Number one, given the format, we're going to have questions via the Q&A feature on the webinar. And we're going to ask that if you have clarification questions, you ask them now. If you have substantive questions for which you want to have discussion, we're going to save those to the end. And we will be having a post-colloquium coffee with Daryl at the end. So without further ado, I'm going to turn this over to the very capable hands of Daryl Haggard. Thank you so much.
Thanks, Jedidah. It's a real pleasure to be here. It's fun to be able to still gather, even if we're gathering virtually. So thank you all for joining in. And please do save up your questions or ask them if I say things that don't make sense on the way. Please do ask Jedidah and she'll pass them along to me. So welcome. The talk today is called New Probes of Black Hole Variability. I have sort of 3 broad topics I want to discuss in this colloquium, but I know that I will run out of time because I'm a big talker and I always have a lot to say. So if there's topics that I breeze by too quickly or ones that I don't quite get to during the course of the talk, we can discuss either in the after talk coffee or anytime that you all would like to via email or other chatting softwares. So it's really my pleasure to start. Oops, let's see. Oh, my talk doesn't want to advance. Let's see. There we go. To start by introducing my wonderful research group. So this is the McGill Extreme Gravity and Accretion Group at McGill University, and these are some of the amazing people who have contributed to the science that you're going to see today. There are many members of my group who have moved on, some who are incoming, and so I just want to acknowledge the excellent work that all of these people do as a part of the science that you're going to hear today. So I'm also really lucky to have been a part of a couple of very exciting science breakthroughs in the last couple of years. The one that Jedidah just alluded to with her cool background is the Event Horizon Telescope discovery or first images of the event horizon of the event of supermassive black hole M87. And this was awarded the Breakthrough Prize of the Year in 2019. And also won I put the little breakthrough symbol up here, the breakthrough prize, not just from Science Magazine, which is a sort of press-related one, but also for scientific discovery from the community. And a few years before that, this neutron-star merger, which was the first truly multi-messenger event that we detected. And I'll touch on these two topics a little bit, in particular this one about multi-messenger astrophysics toward the end of the talk if I have time. But I really want to start off today talking about supermassive black hole variability. So this is one of the probes of supermassive black holes in particular and black hole astrophysics in general that's really helping us start to understand how these systems work, how they evolve in time. And my focus today will really be on Sagittarius A star, and I'm going to talk about some of the different variability diagnostics that we have. So I was at a workshop with one of my grad students, actually Hope Boyce, who's at the group in McGill, and we were discussing with members of the Event Horizon Telescope which sort of plots they thought were the best for showing off black hole variability. And my colleague Jeff Bauer said, oh, well, I know the best plot for you. You'll notice who's the first author on this paper. So Jeff Bauer loves his own plot. But it is a very nice one to show you sort of what timescales are relevant for black hole variability. So this is a plot here of the time scale for variability in days versus the mass of the black hole. You'll see a few of our favorite black holes here. Sagittarius A star is the supermassive black hole that resides at the center of the Milky Way galaxy. You'll see it's on the low mass end here. So it's down here towards 10 to the 6, around 4 times 10 to the 6 solar masses. And correspondingly, its time scales for variability are quite short compared to the others. So you're talking about something less than a day. Typically, Sagittarius A star varies on something like hour-ish time scales. The other black hole that I'll highlight, because I'll talk about it a little bit today, is M87. This is the supermassive black hole that was the subject of that Event Horizon Telescope discovery. You'll notice it has a black hole that is several orders of magnitude larger in mass, and that the timescales that it varies on are correspondingly also larger. And so what this means is that when we design surveys to try to study black hole variability, we have to be cognizant of the fact that the timescales for one black hole might be quite different than those for another. And so the things we want to learn from these black holes have to be teased out sometimes from very different types of observations. So I'll start off talking today about some of the really cool work that we've done using X-rays. So this is the Chandra X-ray Observatory. Many of you have been introduced to Chandra by Jedida and Ryan Hickox there at Dartmouth. And I'll talk just a little bit about some of the contributions that Chandra made to M87's, this really beautiful Event Horizon Telescope discovery of M87. So this is the, let's see here, here is the Event Horizon Telescope image. So this is a horizon scale, very, 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 very small scales. I'm sure you've heard some of those analogies about if you were to put an orange on the moon, that's the kind of imaging capability here. And the other thing you may have seen, which is one of my favorite comics of the last year, is the XKCD comic that sort of places our solar system on the scale of this black hole image here. So this is something roughly the size of our solar system. So Pluto's orbit fits comfortably inside the ring of this black hole Event Horizon Telescope image. But if you zoom out, you start to see that there are structures. These are all radio images. So this is a sub-millimeter image, and these are radio images. You start to see the base of the jet, and you can kind of see the two walls of the jet. This jet is actually angled somewhat toward our line of sight. So we're sort of looking down the barrel of the jet toward the supermassive black hole. Those jet structures become even more prominent as you zoom out. And then on the largest radio scales, you can see this beautiful extended structure that then smashes into the intergalactic medium here and creates these beautiful lobes. So tracing out some of those long wavelength structures in the X-ray is also very interesting. Here you actually see the hot X-ray gas surrounding M87 much more clearly. You can see some beautiful filamentary structure in the X-ray. M87 is what's known as a brightest cluster galaxy. So it is the brightest galaxy in the Virgo cluster, which is one of our nearest galaxy clusters. And you can see this beautiful jet traced out in the X-ray as well. And you can see a very prominent knot here, which we've been studying its variability for a long time in the X-ray. And buried way down in here is this beautiful supermassive black hole. So the X-rays in this case were really valuable for helping us understand the total energy budget of M87 during the Event Horizon Telescope imaging observations that helped rule out certain spin parameters and certain orientations for the black hole. So this multi-wavelength approach was really indeed very helpful for us understanding some of the jet properties and the overall energetics of the accretion flow during this really phenomenal observing campaign with the EHT. So I'll come back to talking about EHT a little bit again at the end of this section about supermassive black holes. But I will tell you that the sad news is that the last 2 years we've had to cancel the Event Horizon Telescope observing campaigns. Last year it was due to some hardware and other sort of constraints at a few of the sites in the array. And this year, the COVID-19 crisis that has hit all of us in our different ways also closed down many of the observatories that would make up the array. So the observations we have of M87 and Sag-A-Star, which I'll spend some time talking about, are mostly from 2017 and 2018. And we're really excited to get back on the sky and observing supermassive black holes with the Event Horizon Telescope again next year. So moving right along, I told you that I'm going to spend most of my time talking about Sagittarius A*. That's the supermassive black hole in our Milky Way galaxy. So the question is, everyone knows, or maybe if you don't know, let me tell you now, Sagittarius A* is one of the other targets for the Event Horizon Telescope. So what gives on Sag-A*? So Sag-A* is a really cool black hole. It's the closest supermassive black hole to us. Some of you may have heard a press release a week or two ago about another black hole that's very close by. For folks who are not astronomy aficionados, that black hole is what's known as a stellar mass black hole. So it's a very small black hole, where Sagittarius A* is a supermassive black hole. And so we only have, we think, approximately one supermassive black hole per large galaxy. Sometimes you might have a galaxy merger that could give you two supermassive black holes, but in general, one supermassive black hole, one galaxy. So the Milky Way's supermassive black hole is Sagittarius A*, and I'm showing you what's known as a spectral energy distribution plot here of Sag-A*. So this is the energy, and this is the luminosity, excuse me, and the frequency at different wavelengths. I've marked out radio, millimeter, infrared, and X-ray. And you can see here, these are some observations here in the colored points, and then a few models marking out Sag-A*'s emission at these different wavelengths. And I'll point out in particular in the infrared here and in the X-ray here that these are different times. So this is the X-ray emission from Sag-A* at one moment in time. This is maybe a year or two later, and you can see that it is highly variable. And so these very interesting variability features are one of the things my research group has spent a lot of time thinking about over the last couple of years. In the X-ray, these are really quite distinctive variability structures, which we refer to as flares. In the infrared, the flaring behavior is not quite as distinct between quiescence and flare. I'll show you plots of these in a second. But in the infrared, it's more of a flickering. So Sag-A* flickers a little bit like a candle. So it's a continuous variability rather than a distinctive flaring behavior. So you'll see those phenomena in some of the light curves I'm going to show you coming up. So here I'm marking with arrows just this very distinctive variability we observe in our supermassive black hole. So this is the X-ray perspective on Sag-A*. So this is the X-ray emission in the vicinity of the galactic center. This blue circle here is showing you the rough kind of capture radius, the area from which Sagittarius A* collects gas and grows a supermassive black hole, or sometimes that gas is being blown away from the black hole by the energetics of the accretion flow. If you zoom in a little bit more, so that once again, we're looking at something that's sort of solar system size scales here. You can see this is the hot gas immediately in the vicinity around Sagittarius A*. And these green contours are showing you the concentration of emission around Sag-A* during a bright flaring event. And so to put all of that in a little bit more context, this is a very zoomed out picture of the galactic center. I'm down at the bottom here, and as we zoom in, you start to see stellar structures. These are the S-star orbits, which some of you have probably seen videos from the Getz group or the Max Planck group of these stars orbiting around the supermassive black hole. So those Keplerian orbits are one of the ways we get a very exquisite measurement of the mass of Sagittarius A*. And if you zoom in further, you can see this hot X-ray gas. The artist that was working with us to create this image is depicting it as a kind of a fuzz. So this hot X-ray gas here is basically showing you an artistic impression of this hot X-ray gas. So the stars that are orbiting around Sag-A* are punching through this very hot accretion flow in our own galactic center, and perhaps driving some of the variability around the supermassive black hole. And here now, at the very smallest scales, you're seeing a simulation, a GR MHD simulation showing maybe an accretion flow in a jet. So we're still working on trying to probe the physics way down here at the small scales using the Event Horizon Telescope and the gravity experiment, which I'll talk about in a little while. So these are the kinds of things that we want to measure when we go out and we use these very precise instruments, the X-ray, the submillimeter, and the infrared. So this is a plot here of density on the left vertical axis and black hole accretion rate on the right vertical axis as a function of radius along the bottom. And we're basically trying to use our beautiful, amazing telescopes to get quantitative measurements of what the accretion flow looks like at all these different radii. So this is sometimes known as a temperature density profile, or just a profile of the accretion flow to understand the physics at play at different points in the accretion flow. So out here at 0.7, so kind of larger regions away from the supermassive black hole, most of the hot gas there and the temperature and the density of that gas is determined by stellar winds. So I showed you those stars orbiting around Sagittarius A star, punching through that hot gas. Actually, that hot gas is coming from the stars themselves. The stars emit winds. Those winds are kind of filling that capture radius around Sag A star with their hot gas. And then that gas is subsequently accreted onto the supermassive black hole. As you move in a little bit further, the gas is becoming a little more organized. It's not quite a flattened accretion disk, but an accretion flow. And so in at these slightly closer radii, you start to be probing the hot X-ray gas. As you march in further, you can sometimes study individual objects. G2 is one particular object that was orbiting around Sag A star, and you can try to watch their orbits and see if you can detect drag forces or other interactions between that hot accretion flow and an individual object as it's orbiting. And then you get into some of the more specific radio observations or submillimeter observations made near the horizon scale, again, by gravity and the Event Horizon Telescope, and I'll talk about that a little bit coming up. So we are basically marching in toward the event horizon, trying to measure what the accretion flow looks like at each of these different radii. So out at those larger radii, at the sort of outer edges of that plot that I was just showing you, we are probing that accretion, that part of the accretion flow using X-rays. And one of the things that's very cool that the X-rays can do is show us these beautiful flares that I mentioned before. So here I'm showing you again, that multi-wavelength image of the entire region around the galactic center. So this is a very zoomed out picture of all of the stars and gas and dust in the vicinity of the galactic center. And then zoomed in the middle here, you see an X-ray image of the region around the supermassive black hole. So one caveat that's important, you'll see if you look carefully at this little zoom in panel, that there's a persistent source, which my pointer is pointing to right now. And then you'll notice that there's a bright flash, and that bright flash is slightly offset here from the persistent source. So in fact, when you look toward the galactic center, as we were doing a few years ago, there are two different sources around these observations. A magnetic neutron star went into outburst. It is extremely close in projection to the supermassive black hole. So the persistent source you're seeing is a magnetar, a magnetic neutron star, and the bright flash you're seeing is actually from the supermassive black hole from Sag A star. This is a little easier to visualize here if you just look at the static X-ray images. So this is one observation taken in September 2013, another observation taken about a year later in October 2014. And this source circled in yellow is this magnetic neutron star in all of our panels. In the left-hand panels, you're seeing Sagittarius A star during one of these bright flares. In the right-hand panels, you're seeing it during its quiescence, just its normal sort of quiet moments. And so these bright flares were the subject of several different inquiries that my group has pursued over the last few years. So this is that brightest flare, the one that was on the top from September 2013. And you can see this flare, this is quiescence down here at the bottom. We're looking here at light curves. So this is time on our horizontal axis and counts. You can just think of this as a sort of a flux from the source along the vertical axis. This is the September light curve and the October light curve. So these very bright flares, as I mentioned, are quite distinctive. So this is the quiescent state of Sagittarius A star when it's very quiet. And you can see the flares are really easy to detect. They stand out. They're quite different from the usual emission from Sag A star. Marked here in orange, just so that you all know, is that magnetic neutron star. And you can see it's not responsible for the flares. It's just kind of bubbling along, doing its own thing. And that's the case in both of these panels. So this is a population of flares over here in this plot. You can see this is F1, that very bright flare in September 2013, and F2, the slightly fainter one in 2014. These two flares are the brightest ones we've ever seen from Sagittarius A star. This is a larger population of around 40 flares that were observed the prior summer in 2012. From also using the Chandra X-ray Observatory. So this bright population of flares is not as well explored as some of the fainter flares. That's partly because the bright flares are statistically just less common, but they seem to be in general very similar as far as their energetics, their spectrum, their other properties between these bright and these faint flares. So this is a very, very interesting variability phenomena. You'll remember I started by talking about Sagittarius A star and M87. M81 was on that plot of time scale versus black hole mass. So we're quite lucky, actually, that Sagittarius A star has just the right mass that allows these flare timescales, this variability timescale, to be of order a few hours, something less than a day. That fits our sort of human observing timescales very nicely. It makes it easy for us to watch a source and see this very distinctive flaring feature. So that's just a happy circumstance from nature. So we wanted to know, that's great. Okay, so Sagittarius A star has beautiful flares in the X-ray. What's going on in other wavelengths? So we also looked during several of those Chandra observations with the radio observatory, the Very Large Array. So these are several of the dishes from the VLA. And you'll notice this is that very bright flare I showed you before. The green points are showing you the X-ray emission. And this is what the radio emission was doing at that same time. So similar to the description I gave you for the infrared variability, the radio has almost continuous variability. And so we spent quite a bit of time trying to understand whether or not we were seeing a correlated variability between the X-ray and the radio. If we were seeing that correlated variability, it looks like there's actually some sort of interesting cross correlation. Let me just point you down to this fourth bullet point here, where the X-ray peaks first and the radio peaks later by about 125 minutes, so a couple of hours. And that has been seen in a few other observations, but I want just sort of, oh, and you can see that here in the cross correlation. This is a cross correlation diagram showing that peak here at about 125 minutes. But in particular for grad students who are thinking about data analysis and all of the different ways that you might think about using different data streams to understand the physics of the sources you're studying, we were a little skeptical. If you go back here, you'll notice, so these gray parts in this plot are showing you regions where all of the telescopes are looking down toward the horizon. And that means that many of the telescopes are looking at the back of the other telescope, plus you have more impact from the wind and other things. So these are less reliable observations here at the edges. You also notice that we don't really necessarily pick up the maximum peak or follow this radio peak into its decay. So we don't quite know where it peaked. We're not exactly sure whether or not the onset of this radio rise is connected to the X-ray variability or not. So being skeptical, we took all of our observations. We took the radio data and the X-ray data from a variety of different observations spread out over the course of a couple of years. And we just cross-correlated everything with everything else. And so the panels you're seeing in yellow down the diagonal here are cross correlations of truly simultaneous light curves. So where the radio and the X-ray light curve are actually being collected at the same time. And then all of the off diagonals are places where the observations were not being collected at the same time. We just cross-correlated them to see how easily we could get a spurious signal. And so you can see here, this is that September 2013 observation. And you see when we cross-correlate our X-ray light curve against almost any radio light curve, we get a fairly strong cross-correlation peak. And that's partly because the radio varies a lot. It's varying all the time. So if I take one of my beautiful distinctive peaks in the X-ray and I cross-correlate it with almost any radio light curve from Sag A star, I'm going to find some interesting cross-correlation timescale, which is not actually physical. It's just a sort of a feature of how the two data sets knit together. So this was a little bit, not discouraging exactly, but I think it gives one pause about how easily we can interpret the timescales and the variability characteristics when we move from one wavelength to another. So I'll just say here that we had hints perhaps that the shorter wavelength is leading the longer wavelength. This may be consistent with some sort of a model where you have a little bit of ejecta from the black hole, and that's expanding in time. And we may see some evidence that stronger X-ray flares lead to longer time lags. But I will just give you this caveat again that these are fairly weak claims, given that the X-ray and radio cross correlation was maybe not quite as robust as we'd like it to be. And that's this claim, this statement at the end about the statistical evidence being fairly weak in this case. So this motivated us to then move on and think about two wavelengths that are a little bit closer together on the spectrum, the infrared and the X-ray. In that early SED I showed you, those two wavelengths were the ones that seem to be varying the most. And so perhaps those are the places where you'd expect the variability to occur together, or if they occur at different moments, that can tell you something about the physics driving that flaring behavior. And so we undertook a campaign to take two space telescopes in this case. So now we're using the Spitzer Observatory and the Chandra X-ray Observatory. And in this case, we were very lucky to convince two different telescope allocation committees to try to point toward the galactic center at the same time. So this is very cool because the space observatories, in this case Spitzer and Chandra, both have very long orbits, and so they could look toward the galactic center uninterrupted for a fairly long continuous piece of time. So the observations I'm going to show you here are the result of these campaigns. These first two panels here are showing you once again light curves. So these are time along the horizontal axis, flux density along the vertical axis. This is a very beautiful piece of work done by a graduate student in my group, Hope Boyce. So you're seeing here, the gray points are showing you the Spitzer extractions for Sgr, and then our kind of running average in the red. The purple light curves up at the top are the Chandra observations. And the little orange lines that you might just be able to make out are our flare detection algorithm. We use an algorithm called Bayesian blocks, searching through the X-ray light curves, trying to detect flares. And so these top two panels were our first campaigns using Spitzer to look at Sgr, and we had only partial coverage from Chandra. So you'll see only very short light curves from Chandra. But here in the bottom four panels, you can see what we were really shooting for were these very long campaigns where we observe in the infrared and in the X-ray continuously, simultaneously for 24 hours or sometimes longer. This gets you a little bit out of some of the trouble you might have had with the radio and the X-ray, where you can't tell where the radio actually started to rise. You can't tell when it turned over and started to decay again, where you might have a long X-ray light curve and a short radio light curve. Now we have many examples of beautifully continuous and very long infrared and X-ray light curves. So these are observations, as I said, of Sagittarius A star. You can see here marked with numbers 1, 2, 3, 4 are four brighter infrared events that seem to correspond to the 4 detected X-ray flares. So here you can see an X-ray flare here, here, and here. You'll notice 2 of these events are in the same light curve. So during one of the observations, you'll see that again in the next panels where I zoom in a little bit. So here again are those same light curves, just zoomed in, really focusing on the flaring events. And in the bottom 3 panels, you're seeing once again that cross correlation where we actually want to see temporally how close in time are these 2 peaks in the infrared and in the X-ray. And so you can see here the red line is marking 0. So a 0 measurement would indicate that the X-ray and the infrared were fully simultaneous. We see here again, so for the peak to be shifted slightly to the left of that line means that the X-ray slightly preceded the infrared, and we see a slight hint of that in every case here. So you'll notice that's marked by a negative number. That means that the shorter wavelength is coming slightly before the longer wavelength. I'm going to skip back for 1 second to the previous slide and just point out one thing I forgot to mention. And that is that the infrared, you'll notice, is much more variable than the X-ray in general. So we have many instances where we see some infrared activity. Maybe this is the best example where my pointer is here. So there's heightened infrared activity, but there's really not that much going on in the X-ray. And so this is something that's been seen in Sgr for a long time, where we see more variability in the infrared than in the X-ray. That may be because the X-ray has this sort of underlying accretion flow, which causes there to be an overall sort of X-ray flux that tends to wash out faint X-ray flares. So that's one possible explanation for why the X-ray has less, fewer peaks than the infrared, or maybe the two are slightly conflated by different, probing slightly different parts of the accretion flow or different physical processes. Okay, so here's this hint, and then Hope has taken this and kind of put it into a nice plot and also culled all of the different measurements from the literature. And so these here are showing you the flares from this work, from these beautiful long Spitzer, continuous Spitzer Chandra light curves, Chandra and Spitzer light curves. This is the first flare, the second flare. This is that third observation that contained two flares together, and these are those two flares treated individually. And you'll see here, this line here once again is marking 0, so where the X-ray and the infrared occur at the same time. And you'll notice that in general, the points tend to be sort of biased toward these negative numbers, these negative time lags, which mean that the X-ray is slightly coming before the infrared. But the error bars are 1 sigma error bars here. So really these are statistically consistent with no lag between the two light curves. So we're still working on a whole new beautiful data set, and we have several more of these 24-hour data sets, and we're hoping to kind of pin this down a bit better. All of the points that you're seeing here from the literature also show consistency with no time lag. So why does this matter? So here I'll put just my little guide up here. So this means the infrared would lead the X-ray. This means the X-ray leads the infrared. So different physical mechanisms and different physical processes might lead the infrared and the X-ray to have sort of different phenomenology in their variability. So for example, if you thought all of the variability from Sag-A was due to gravitational lensing, maybe you've got some hot spot in the accretion flow, it passes over a gravitational, some sort of gravitational perturbation, a caustic, and that causes this brightening. So we know that gravitational lensing happens the same way at all wavelengths. And so you would expect to see the infrared and the X-ray change simultaneously if you were just seeing flares as a result of gravitational lensing in the accretion flow. If, however, there's some other kind of process, maybe you've got a little planetesimal, a little asteroid or something that's in the accretion flow, it's falling in toward the galactic center, it's getting shredded apart, that material might heat differently as it's being tidally disrupted and accreted onto the black hole, and that might have slightly different signatures in the X-ray and the infrared, leading to a different diagnostic from the variability. So one of the things that Hope concluded from looking at these observations is that it looks like the infrared and the X-ray are both very consistent with a synchrotron particle acceleration mechanism. So this is an acceleration mechanism which is, roughly speaking, kind of like a flaring event you might expect to see on the surface of the sun. So maybe you have magnetic fields threading through the plasma around the black hole. They experience magnetic reconnection, which accelerates those particles, and that could lead to a slight lead for the X-ray emission over the infrared emission. And this has been predicted by several different works who are trying to think about and figure out what sorts of underlying physics might actually be able to explain these flares. So these lags are consistent with synchrotron models, but they can't completely rule out synchrotron self-Compton models, and they may actually help us get rid of inverse Compton models. So just to remind people, synchrotron radiation is where you have electrons spiraling around magnetic fields. And so that's why these are very common. This is a very common process when you're dealing with a magnetized environment. Synchrotron self-Compton, so now you have Comptonized material, and maybe you have particles that are actually heating up and Comptonizing their own electrons and photons. And so each one of these different models has been put out there, and it's hard to rule them out without more precise observations. And so what we'd really like to see now is to take this phenomenology we've put together and to really march down in toward the event horizon and see whether or not we can trace out some change in the morphology of the accretion flow that goes along with all the energetics of these variable signatures that we've seen so far. So that's the next attempt, is to march down toward the event horizon. So just to mix things up a little bit, here's that event horizon scale picture of M87. Again, this is not Sag A star. We have not yet shared with you a picture of Sag A star. And I'll tell you one of the reasons you haven't yet seen this picture for Sagittarius A star. And that is exactly because M87, if you think back to that plot, M87 is a very massive black hole, and its variability timescales are sort of like months to years. Remember now, Sag A star is several orders of magnitude less massive. Its variability timescales are hours, which means when we go out with the Event Horizon Telescope to try to observe Sagittarius A star and create a beautiful image like this one, what we actually see is something that varies in time. And that makes the image reconstruction that went into making something like this image way more difficult. So I spent an entire week last week in an imaging workshop where everybody just battled all the different systematics between the observatories, which might give you variability, the atmosphere, which might give you variability, the black hole itself, which might give you variability, and how to piece all of those different things out so that we can actually see, okay, have we captured the event horizon of Sag A star? Can we say something about structures moving around the black hole, or some different energetics happening in the vicinity of the black hole? Okay, so these are the two instruments that are really pushing really hard down toward understanding what's happening near the event horizon. The Event Horizon Telescope I've mentioned several times, and I'd like to spend a little bit of time talking about the VLT gravity experiment as well. So these are really beautiful high signal noise observations happening at sub-millimeter wavelengths for the EHT and at infrared wavelengths for VLT gravity. You can see their sort of rough wavelengths and the baselines. So B stands for baseline. So the Event Horizon Telescope is an array of telescopes spread across the globe. The gravity instrument is in Chile. This is the Very Large Telescope Interferometric Array. They've linked together these 4 observatories into an interferometer. So their baseline is more like 100 meters rather than 10,000 kilometers. And that baseline changes how sensitive you are to very small scale structures. So the resolution, the ability to tell 2 different points in the sky apart for the Event Horizon Telescope is around 20 micro arc seconds for the Event Horizon Telescope, and more like 4 milli arc seconds for gravity. So gravity doesn't have quite the resolution that EHT does, but it's working at the infrared wavelengths, which I've been talking about before, and can give us some interesting insights for those slightly larger scales. So this is a press release image. Hopefully my mouse will actually turn the little press release movie on. Yeah, here we go. So this is from a press release that the Gravity Collaboration put out a couple of years ago. So they are actually taking observations of Sag A star at near infrared wavelengths. And what they see, so this is a simulation, not a real movie, but what they see is the centroid, the center position of Sag A star actually moving around on the sky. And when they interpret that through the lens of GR MHD simulations, so that's general relativistic magnetohydrodynamic simulations, they can model that motion of the centroid of Sag A star using a few flares. And they see that centroid move at specific times that seem to correspond to flaring behavior from Sag A star. And so here is their beautiful simulation trying to show what perhaps might be happening in the accretion flow during those observations. So they detected 3 NIR flares with some of this positional information, which we've never had before. And they found that those energetics for those flares are consistent with those flares coming from very close to the so-called ISCO. So this is the innermost stable circular orbit. So this is sort of the point of last return, the point of final orbit for particles just before they fall into the event horizon. The flare durations are something like 30 to 90 minutes. And so this is sort of consistent with the electron cooling time for material that was in some sort of differentially rotating disk near the black hole. And so these observations are pretty exciting. This is sort of pictures of different ways that that centroid has moved around and how that might map to interesting changes in the accretion, actual disruptions of material as it goes around the black hole. I'm going to kind of move through this a little bit more quickly, but one thing I just want to point out is that these models that they've built are consistent with hotspots that are moving fully at 1/3 the speed of light. So remember remember, we are probing the strong gravity regime here. So everyone wants to know, is GR still right when you get down really close to a supermassive black hole? So far, none of the observations that we've made as astrophysicists have showed that it's wrong, but that doesn't mean that we won't keep pushing and keep trying to figure out where the limits of GR might be. And pushing into regimes where you've got material moving at a third the speed of light is pretty exciting. And so these orbital radii that are consistent with these flares are really, really close. So 6 to 10 gravitational radii from the supermassive black hole. Of course, black hole spin is a great uncertainty. The black hole, as it spins, can frame drag or also move the reference frame around with it as it's going. And so different solutions for the black hole spin can lead to a lot of different parameters for the orbits of material. And so one of the big degeneracies in the models right now for understanding what's happening near Sgr star is how the black holes spin and the overall orientation of that spin to our line of sight are impacting the observables, the things we actually see. Okay, so one thing I just want to point out because it's fun. So this is that very bright X-ray flare I showed you before. It's a little bit more stretched out and elongated here. So this is that Sgr star bright flare and the magnetar. And one thing that's kind of interesting is that the difference between these, this is a double peaked flare. We see quite a few double peaked flares from Sgr star. And the difference between those two peaks is about 30 minutes. And the difference between the two peaks in one of the gravity flares, so this is an infrared flare from gravity, is around 40 minutes. And so these are looking like these double peaked phenomena are really quite similar between the infrared and the X-ray, maybe hinting again at something like synchrotron as being the source of the flaring activity, which is really leading to sort of similar timescales and phenomenology for the X-ray and the infrared observations. So we're still working very hard. I mentioned to you already that the EHT campaigns for 2019 and 2020 were both called off for a variety of different reasons, but we're hoping next year to get back on the sky and have gravity, the Event Horizon Telescope, and then a whole suite of other multi-wavelength observatories, NuSTAR, Chandra-Spitzer, VLA, etc., all observe the galactic center at the same time so that we can try to map changes at the horizon scale to changes in the other wavelengths to understand exactly which thing is driving which and what the different sort of energetics and physics are that are guiding the variability for this supermassive black hole. And the hope, of course, is that if we can take this incredible laboratory that is Sagittarius A star as some sort of an indication of what happens in accretion flows near black holes, that we might be able to then extrapolate that to other systems that are similar to Sgr star, other black holes that are feeding or growing throughout cosmic time. So this is one of our sort of most local laboratories for studying supermassive black hole variability and supermassive black hole growth. Okay, so I'm going to move on. This is basically just saying the same thing. We're very excited about the HT. So it's very fun to try to figure out how we can get these campaigns organized, and they are quite a bit of work to pull together. Okay, so let's see. All right. So this is just a quick summary to say that we've been working on these multi-wavelength flares for a long time. I mentioned that the flares look very similar one to the other, whether they're bright or whether they're faint. And we're working really diligently to try to get data from multi-wavelength campaigns together and to use these to probe the accretion flow, the plasma physics, to understand the conditions of the gas, the density, the temperature in very, very close, and to use that to help us understand the particle acceleration mechanism and potentially how that's tied to the structural changes near the event horizon. And of course, eventually to use those things to probe general relativity and magnetohydrodynamics and all of the other interesting physics that we are pretty much limited to simulating in a computer right now. Okay, so I'm going to move through a couple of other topics. I think I'm probably getting close to my time here, so let me just go through these rather quickly. Two other areas where we've been trying to build insight into black hole variability are by taking supermassive black hole variability and trying to understand how it might connect up to variability in the lower mass, the smaller stellar mass black holes. And so one of the ways that we hope to do that is to understand how accretion flow, material flowing in and material flowing back out, whether it's through jets or winds, how those two things are actually linked together, how they're tied. And so the these connections, sometimes called disk jet connections, are interesting to look at in X-ray binaries, where we can study them on pretty interesting short time scales, and then to try to extrapolate to larger time scales. So as I mentioned, we see accretion disks, which have very, very high temperatures often and can be probed using X-rays, and then the outflows are often traced out by radio wavelengths, longer wavelengths, because they're often guided by the synchrotron radiation of electrons spiraling along these magnetic fields. So what we'd like to know is, can we actually realistically use X-ray binaries, the stellar mass black holes, where we can watch this disk jet connection evolve in real time? Can we use those as an analog to more massive black holes, to supermassive black holes? And so two members of my team, actually several different members of my team, 3 or 4 maybe even now, led really by John Runn, who's a postdoc in my group and moving on to a faculty position this year at Bishop's. This group is looking at a really cool type of AGN called a changing look quasar. I'm going to skip over this slide. So changing look quasars are this very interesting subclass of supermassive black holes, of accreting supermassive black holes, that seem to change from being kind of traditional, highly accreting quasars, which we typically identify by using their broad emission lines. So you can see, if you look at this black spectrum, it's got this very broad very broad emission line. And then a few years later, we go back and we look at it again, and that broad emission line has disappeared. So just for those of you who are not astrophysicists, quasars are not supposed to do this. We would expect, if we just take our basic understanding of accretion physics, that it would take an AGN, something that's got 10 to the 8 solar masses, that it should take it around 10 to the 5 years to undergo a transition like this one. But these two spectra are actually only taken about 5 years apart, 5 to 10 years apart for most of this class of sources. So this time scale is just way too quick. And so members of my team have been working really hard to try to understand what's going on with changing look quasars, and can we use changes from X-ray binaries, the studies of X-ray binary systems, to understand how these changes happen so quickly. So I probably won't have time to go into this, but I will just point out that we have a lot of really interesting sort of diagnostics based on X-ray binary studies, where we see them change in time as they go from having a stronger accretion disk to a stronger jet and then back again. They tend to move around in this space, which is intensity versus their spectral index, which is just a measure of the shape of their spectrum and the slope of their spectrum at high energies. So this plot, they tend to move around in here as they evolve. And the question is, can we see the same change, the same phenomenology when we look at AGN? And so people have tried to do this with populations and to try to look at different higher mass objects. So just as a reminder, this is a low mass object, or a stellar mass black hole undergoing transitions. And this is now taking this model of stellar mass black holes and modeling and pushing it up to supermassive black holes. And what we'd like to see is, do observations support this sort of transition happening for these higher mass systems? I should say, actually, these beautiful slides I'm showing you now are a credit to a graduate student in my group, Sheng-Yu Jin, who has been working really hard on understanding these transitions alongside John and others in the group. So this is a study that John put out last year, trying to actually look at some sources that might be sitting down here near this transition. You'll see here again, these sort of faded colors are the model scaled up from X-ray binaries. And you'll see here that the observations are looking interestingly supportive of this population, actually tracing out the same behavior as we see in X-ray binaries. And Sheng-Yu has tried to now expand that study, and you can see again, her work is showing some interesting trends that seem to agree nicely with this sort of analogy between X-ray binaries and supermassive black holes. Okay, so just very quickly, I will only touch on this, and then we can talk about it in the Q&A after, because my time is pretty much up. I will just say that there's one other kind of black hole variability that we are just tiptoeing toward, and we haven't really gotten a chance to study yet. So I've talked a lot about Sagittarius A-star and M87. Those are really fascinating, and there's a ton of time domain studies that have gone on for those. And I talked a little bit about spectroscopic variability. People like Jedidah and Ryan and others are experts, and they can talk to you probably for colloquium after colloquium more about AGN variability at a variety of wavelengths, and in particular spectroscopic variability. But we have this new lever to try to understand what's going on with black holes and neutron stars, and that is gravitational radiation. So you're seeing this beautiful sort of artist impression here. And that wonderful discovery from 2017 was of 2 neutron stars colliding and emitting gravitational waves and emitting an amazing electromagnetic signature. So hopefully you all have heard some colloquia about that and heard about that in the past. But the next big discovery that we're hoping for from this is actually not just 2 neutron stars together, but a black hole shredding apart a neutron star. And so we got our first sort of taste of this. I will say this detection has not been fully multi-messenger yet. So we have the first detection. Oh, this is this beautiful neutron star merger, which I'm going to skip over. But this source here, GW 190814, so this is discovered in August of 2019, was an amazingly well localized gravitational wave source. And this is one of the first really compelling LIGO detections of a black hole neutron star merger. I will point out that because of this, there are some vagaries about the interpretation of the gravitational wave signal, and it could actually be a low mass black hole and another low mass black hole, and one of them is just sort of maybe consistent with a neutron star. So we're not quite sure yet what's going on. And I'm going to skip over this because I can see in my chat window that Jedidah is telling me to pipe down. But I just want to let you all know that we did, many of us in the community followed up this really interesting event to try to see if we could find an electromagnetic counterpart to this first proposed black hole neutron star merger, including a graduate student in my group, Nick Vieira. And we hope that these might have signatures similar to neutron star mergers called kilonovae, so it's sort of explosive, tidally disruptive material. And we did a really deep search, which I'll just sort of flash by and we can talk about it again later, a really deep search using the Canada, France, Hawaii telescope to try to localize an electromagnetic counterpart to this gravitational wave source. And we had no detections, but we did make some really beautiful deep observations that help constrain those models for future observers. And we also put in place this really awesome framework to be able to do this more rapidly next time around. So our team was not alone. There was no electromagnetic counterpart detected for this proposed neutron star black hole merger, but we hope LIGO Virgo, when we can all get back online, get observing again, we'll make many more discoveries, and hopefully we'll be able to follow one of them up and find a counterpart. Okay, so, and I will just say that we're coming into an era, I'll sort of end here. These are pictures of, the sort of timeline for LIGO and Virgo and Sgr. These are all gravitational wave detectors, and also LIGO India, which will give us even better localization for gravitational wave sources. But also LSST is coming online soon. And so this era of sort of variability as a probe, as a diagnostic for many different systems, not only for black holes, but also, powerfully for black holes, is really going to kind of just keep sweeping through our community. So variability as a way of trying to get at and study the physics of these astrophysical objects is going to be growing in importance over the next many years. All right, I'll leave it there. Thanks, everyone.
Thanks so much, Daryl. That was a lovely talk. So if you have questions, please do put them in the Q&A chat now, and we will get to them just as soon as we can. And while I'm waiting for folks to type out their questions, Daryl, I have a question for you. Actually, going back to your gravity observations and the relationship with the NIR flares, and potentially trying to tie that result to magnetic reconnection. I thought that was a really interesting result. And I was going to ask you about polarization, and you flashed that slide really quickly, showing the NIR flares and polarizations. And I wonder if you could just take a second to walk us through that. Because that was I wanted to make sure there was, because as we know, polarization can be a really good distinguishing feature between, say, magnetic reconnection and synchrotron processes.
Was that here? Where was I?
Yes, that'll work.
Okay, yeah. So polarization angle is, again, just for folks that are not used to thinking about polarization. So this tells you something about how the magnetic field is oriented in your observation. And in particular, the polarization angle can be really illustrative for understanding jets and outflows. So Jedidah, I'm not sure I'll completely answer your question here. So polarization, actually, I think our very first polarization papers for M87 from the Event Horizon Telescope will be out in the next month or two. So you can see how the polarization angle might change over time. So if you're looking at some sort of a jet structure, and imagine that jet structure kind of pointed toward you, As material flows around and along that jet structure, you might expect the polarization angle, the angle of the sort of polarization vector as things rotate through that jet will change with time. And so we can actually watch as things move around, we can see the polarization angle. So if I'm a little dust particle and I'm oriented like this, maybe I'm rotating as I go around the black hole, we can see that polarization angle change in time. And so you can see here, I didn't really do it justice in my plots, but here, yeah, here we go. So this is a polarization angle. This is actually seeing how the polarization changes in the infrared during the course of a flare. And so this sort of lends credence to something actually orbiting, going around and changing its polarization angle as it orbits, rather than just something that was sort of over here flashing and then fading again. And so polarization is something that EHT hasn't quite presented to everybody yet, but it's coming out, and gravity is actually doing a pretty good job of getting at the polarization angle. I'm not sure if have I answered your question, hopefully, yet?
No, but we can talk offline about it because a question
Yeah.
came in. I want to leave room for it.
Yeah. Okay.
So this question is, why are the X-ray flare signatures double peaked? And it's from an anonymous attendee.
Okay, yes, that's a good question. We don't know. There's a bunch of different possibilities. So probably the most like mundane but likely possibility is that X-ray flares happen on average about once per day. And as you saw in one of those plots that I showed you from Hope's beautiful work, there sometimes are 2 flares in a single observation. And you know, those 2 flares don't necessarily have to be hours apart. They might be just a few minutes apart, and then you might just end up with one superposed on top of another. So that seems totally reasonable. It's possible. Another possibility is actually that you might get a little bit, so if you've ever looked at a lensing light curve, as something passes over a gravitationally lensed caustic, you can get a rise and a fall and a rise again, and then a decay. And so this could be some indication of some sort of a gravitational lensing signature, might give you a double peaked flare. But we as yet don't really have a for sure explanation of this. Let me just throw out there one other thing. If any of you have ever looked at these amazing SOHO satellite images of our sun, so this is looking at our sun in the X-ray, you can see that when you have a magnetic reconnection event, so 2 magnetic fields get forced too close together and they basically break and reconfigure, that actually can catalyze, the energy injection of that can catalyze another reconnection event and another one and another one. So when you look at magnetic reconnection happening on the surface of our sun, you can actually see there are often little sort of chains of events where maybe one flare is sort of initiating the next and initiating the next. So these are all different ideas about why we might get multiple peaks in our flares, but we as yet haven't really, I think, dived in and gotten enough kind of insight into exactly what the timescales are and whether or not they're repeated. We have a couple of examples here, but we don't have a whole population to study just yet.
Great, thank you so much. And we're right on time. So thank you again, Daryl, for a very interesting, lovely talk, including hints into what we may see soon from EHT. That's very exciting. So we're going to transition now to our post-colloquium coffee time. You should have the link in your email. Please do join us there. Daryl will be there for about 30 minutes, so we'll look forward to seeing you over there. Thanks again, everybody, for attending this week's colloquium. We'll see you next week.
Thanks.